So welcome back. I want to talk about what dose response information we have, which is for SARS-CoV-1, and show you how we validated it. And the presumption, until further data comes in, is that this is a good starting point for estimating the risk for SARS-CoV-2. So this was a paper published about 10 years ago by a group from my laboratory. Toru Watanabe was a visiting postdoctoral student from Japan that really did the heavy lift on this work. And then my former PhD students, Tim Bartra and Mark Weir, and the collaborator from Japan, Tatsuo Omura. So there were several non-human models for SARS-CoV-1. And the best models were available for two coronaviruses that were administered to mice intranasally. And so you see in this graph, again, dose in terms of plaque-forming units. And response on the y-axis. And the black in the open circles represent two data sets. We were able to pool them together and get a very nicely fitting exponential dose response model given by this equation. You notice here we've defined K in the reciprocal fashion before from what I presented earlier. And in this form, the exponential dose response, K is equal to 407 as a best fit model. The dashed curves represent the 95% confidence limits to dose response. So again, 1 over K in this formulation is essentially the survival fraction in vivo. So roughly 1 out of 400 of the inhaled SARS-CoV-1 viruses caused an effect. This is animal data. Is it plausible for humans? Now, the problem we have with an outbreak data set is very often we don't know the denominator, meaning the number of people exposed, and we might not know or have an estimate of the actual dose that the people who were adversely affected experienced. So rather than a true validation, we do what I've called a plausibility determination. So I believe I referred to this outbreak of SARS previously. This was the cluster in the Amoy Gardens in Hong Kong. And you recall there were differences depending upon what floor in the most affected tower people lived in. But we do know the number of cases. We do know the number of people that lived in each one of those tiers of the high rise. Based on dividing cases by number of residents, we can get an attack rate. And now we basically run the dose response model backwards. Given the attack rate, what is the dose that would have corresponded to? And so, depending upon the tier in the Amoy Gardens, anywhere from 16 to 40 PFU would represent the attack. And this appears to be plausible based on the assessment of how the virus was transported within the plumbing stack of that building. As I said, not a true validation, but a plausibility assessment. So we appear to be in reasonable order to use the animal data to estimate human risk. So let's now apply it to a hypothetical problem with the current virus of concern. Let's say two people are occupying a room. One is infected, the other is not. The room has mixing ventilation, and we measure the virus concentration at 1 virus per cubic meter. Now, based on last week, if I had given you a ventilation rate, if I had given you a emission rate of the virus from the infected individuals, if I gave you information to estimate deposition rate and decay rate, we could calculate what the estimated viable virus would be. But now, to make it simple, I've given you directly the viable virus. Let's say the susceptible person spends 8 hours in the room. What is their estimated risk? You should stop here and think about what I've said in the previous slides and look at your method of approach before you go on with my explication. So here's the first step in the solution. We want to calculate the exposure. An individual is breathing 8 hours per day. We need a breathing rate. Multiplying that by the virus concentration gives us the dose. So 1 virus per cubic meter times 7 liters per minute breathing rate times unit conversions of 60 minutes per hour, 0.001 cubic meters per liter, times 8 hours gives us a dose, again, average of 3.36. Applying that average dose to the dose-response relationship gives me a risk to that individual, the probability that they will come down with an infection from that virus, of 0.008. Now, is this acceptable or not? Well, there are a couple of yardsticks I can give you to put that in a frame, but ultimately it's a risk management decision. In the US, for drinking water with infectious organisms, principally for those that only result in mild to moderate illness, we regard a risk of infection of 1 in 10,000 per year, not per exposure, to be acceptable. For chemical carcinogens in air, water, food, typically an action level of 10 to the minus 4, 10 to the minus 6 risk per lifetime is used. Is this acceptable compared to those? That needs to be addressed. And one variable is clearly going to be the cost associated with reducing that risk, with mitigating that risk. The last element I want to spend time on is incubation time. When does an adverse effect occur? So I'll motivate this, give you some approaches to fixing the problem, how we model it, and some validation efforts. So the motivation is basically given in this curve. And I think with the media discussion around SARS-CoV-2, you've gotten used to seeing curves like this. It's called an epidemic curve. On the x-axis, number of days. On the y-axis, the incidence rate in terms of cases per day that are observed. So both the red and the blue curves on this graph are drawn so that the area under the curves are the same for the red and the blue. Same total number of cases. And in fact, I've also drawn them so that the arithmetic average, the mean time at which cases appear, are the same as well. But we obviously know, and this is the whole flatten the curve issue, that the distribution of the case burden has public health consequences to responders, to the pattern of contagion, in the case of COVID-19, to overwhelming the healthcare system, and to the ultimate response action that can be taken. So there are two questions. If we have an epidemic curve like this, can it be used to help inform a dose response model? Or can we modify our dose response models to predict the time at which disease would actually occur? So I had a student a number of years ago that looked at it. And our starting point are the two dose response models I presented earlier, the exponential and the Beta-Poisson. Except that we look now at various ways of modifying the parameters in the exponential. In this case, the K parameter. In this case, the N50 parameter, to give time dependency. And so now we have a series of time-dependent dose response models where TPI is the time after exposure has occurred. And Dr. Wang, in his PhD dissertation, went through a number of data sets and showed that these models can be useful in fitting data. This is a complicated figure. I'll walk you through it. This is for inhaled mortality in monkeys and guinea pigs associated with inhalation of Bacillus anthracis spores. And so the colors for either the points or the symbols represent individual data sets at individual doses. And you see a couple of things from this. First of all, as dose increases, we see the time at which the onset of infection occurs to increase as well. And second of all, we see a distribution in incubation time that can be modeled by the functions that we talked about. So we don't have a complete validation of Yin's model, but we have a partial validation. There was an outbreak of anthrax in the former Soviet Union in 1979 in the city of Sverdlovsk. This was a paper written by Messelson in Science. You'll notice the date on it. 15 years later, because it took until the fall of the Soviet Union before the complete records of the Sverdlovsk incident became available. But what Messelson reported is given by the points in the right-hand figure. From the outbreak data, those are the days after the incident, which appears to be an inadvertent release from a biological warfare laboratory in Sverdlovsk, occurred. The distribution of times that people became ill. We don't really know the denominator, but we can dimensionalize by the total number of illnesses to get our distribution. And it turns out, with the models that were developed by Wang, that if you get to a sufficiently high dose, the incubation time distributions collapse to an asymptotic value. So we use the asymptotic form of the incubation time developed by Wang. And you see that for the incubation times from the rhesus monkey data, from the cynomolgus monkey data, from the guinea pig data, and all pooled together, given by all but the solid curve in the graph, solid blue curve in the graph, we get reasonable fit to the Sverdlovsk incubation time. So the incubation time distribution is certainly plausible. More recently, I've had a student return to this problem, Dr. Bidya Prasad, who looked at a large number of other outbreaks with other organisms and ascertained whether or not these same dose response time models could be employed. And I'll just give one of her data sets here because Legionella is another pathogen of great significance. She did a similar comparison with a strain of Legionella called Legionella longbeachii, and she found that the beta-Poisson inverse time dose response model gave a reasonable fit and is reported in this figure. And so we believe we have a way to model dose response time that could be useful in predicting epidemic curves. And in fact, this is a good segue to what I'll talk about next week, which will be disease transmission models. How do we really describe the epidemic curve? And how do we potentially depict the effect of interventions on adverse effects that may occur in a population? A reminder that quiz 2 is up for you to do this week. And you have a good week. Stay healthy. And I will be with you next week.